Another helpful way for us to look at the mass of a compound is in terms of the percent mass of each element that's in the compound. So, for example, we look at waters, which we are pretty well familiar with. Okay, we know that water is two hydrogens and one oxygen, which might give us the impression that hydrogen is more prevalent in this molecule than oxygen is. But we also know that oxygen is about 16 times bigger than hydrogen. So, how do we look at this in terms of percent composition? Well, let's do that calculation. Okay, the best way to deal with this is by looking at it like this. So if we want to figure out the percent hydrogen in this compound, what we're going to do is we are going to take the number of atoms of hydrogen and we are going to multiply that by the molar mass of hydrogen. And then divide that by the molar mass of the entire compound and multiply it by 100. Okay, so we have 2 atoms of hydrogen. The molar mass of hydrogen is 1.008, and that's grams, but we're not going to worry about that since all the units are going to cancel out here. Okay, and then the molar mass of water we calculated to be, 18.02. Okay, and then multiply that by 100. So let's put this in the calculator. And I wind up with 0. Actually, no, not 0. Forgot to multiply it by 100. This is going to be 11 point, let's see, 20, I think it is. Yep. Percent hydrogen. And we can do the same thing with oxygen. So percent oxygen is going to be equal to the number of the number of atoms of oxygen present, which is 1, times the molar mass of oxygen, which was 16.00 grams per mole. This time I'll leave the units in so you can see how they cancel out. Divided by the molar mass, which again is 18.02 grams per mole, times 100. And you can see here the grams and moles both cancel out. Okay, plug it into our calculator, and I wind up with 88.80%, which I guess we could have also figured out by just simply subtracting the percentage of hydrogen from 100. Okay, but these are our percentages. Now, going in this direction is a little bit helpful, but what's even more helpful is being able to go from this information, these percentages, to an actual chemical formula. Okay, so I want to introduce 2 different types of chemical formula here. We have the empirical formula, and the empirical formula, if you remember from our previous discussion on this, is the lowest whole number ratio of atoms in a compound. Actually, I should say elements in a compound. Okay, so we can actually figure out the empirical formula for a compound from its percent composition. Now, just to be clear, what we did previously was to figure out the percent composition from the empirical formula. But this is much more useful because there's actually instruments out there that will tell us the percent of each element that's present. Okay, so let's look at an example of this. So let's suppose that we submit a sample to a laboratory, and the laboratory does an analysis for each one of the elements present. And what it finds is that in a particular sample, there are 6.444 grams of boron, and that there are 1.803 grams of hydrogen. And we want to know what is the empirical formula from this information. Okay, well, the way we're going to do that is by working backwards from what we did before. Okay, so what we're going to do is we're going to take the masses of each one of these elements. So we have 1.803 grams of hydrogen. And we know by looking at the periodic table that the molar mass of hydrogen is 1.008 grams for every 1 mole. Okay, we plug that into our calculator. And we wind up with 1.789 moles of hydrogen. And then we can do the same thing with boron. We have 6.444 grams of boron. And by looking at the periodic table, we see that boron has a molar mass of 10.81 grams per mole. And again, we plug this into our calculator to figure out how many moles of boron must be present. And I wind up with 0.596 moles of boron. Now, once we have the number of moles of each element, the next thing is to write out the formula. But for the subscripts, instead of using the actual numbers of atoms, what we're going to do is we're going to put the number of moles. So for boron, we said that was 0.596, and for hydrogen it was 1.789. The next step is to divide by the least number of moles. And of course, boron is going to come back with a 1. And then we take the 1.789 and divide it by the 0.596, and we get 3.001, which is effectively 3. So we get BH3, and that is the empirical formula for this compound. Now, another way that this type of problem can be posed to you would be in terms of percentages. So let's say that we're told that we have a compound that is 30.46% nitrogen by mass. And we have 69.54% oxygen by mass. Okay, and again, we want to figure out the empirical formula. Well, here's what we got to remember, is what does a percent mean? If we're saying that there's 30.46% nitrogen by mass, that means for every 100 grams of nitrogen, there are 30.46 grams. For every 100 grams of the compound, there are 30.46 grams of nitrogen. And for every 100 grams of the compound, there's going to be 69.54 grams of oxygen. So what we're going to do is we're going to treat these percentages as if they were masses. So we're just going to essentially assume that we have 100 grams of total sample. Okay, so for nitrogen, we have 30.46 grams. And if we look at the periodic table, we see it has a a molar mass of 14.01 grams per mole. And then for oxygen, we have 69.54 grams, and that's 16 grams per mole. And just like before, we're going to have to plug this into our calculator. So we take 30.46 divided by 14.01, and we get 2.174, and that's moles. And then for the oxygen, we take 69.54 divided by 16, and we get 4.346. And again, that's moles. Alright, so to figure out what this is, we're going to put down the elements that are present in the compound, and then put down the number of moles instead of the number of atoms. And then divide each side by the least number, so divide both sides by the 2.174. And I get a 1 for the N and a 2 for the O. So this is NO2. Okay, so again, this is another case of us figuring out the empirical formula from mass data. Now, these are empirical formulas, but what about molecular formula? So remember, a molecular formula is going to be the actual number of atoms of each element in a molecule. Okay, so for example, when we looked at the BH3, okay, all this was telling us as the empirical formula was that there were 3 hydrogens for every 1 boron, which means that it could have also been B2H6 or B3H9, B4H12, and so on. Okay, so how do we figure out what the molecular formula is? Well, to figure that out, we need another piece of data. We need to have a rough idea of what the molar mass of the compound is. And it may seem like, well, if we know the molar mass of the compound, well, don't we already know everything we need to know? And the answer is kind of yes, but there are plenty of very simple experiments out there that will allow you to just roughly estimate within a couple of grams what the molar mass is. And that can be enough to figure out the molecular formula. So for example, let's say that compound we were looking at before was found to have a molar mass somewhere in the region of maybe 25 to 35 grams per mole. Well, we can actually figure from that information what the molecular formula must have been. Okay, so if you think about it, we have BH3, and we said that boron had a molar mass of 10.81. Okay, so we take that 10.81 and then add to it 3 hydrogens, which are each 1.008. Okay, and we get 13.8 grams per mole. Okay, now B2H6 is going to be twice that number. Okay, which is going to give us 27.7. Okay, and for B3H9, it's 41.4. But you can see we've already gone past that upper limit there. So the only one of these three formulas that actually fits into the criteria for the molar mass is this guy here. Okay, so we can find the empirical formula with the mass data. But if we're going to figure out the molecular formula, we need molar mass data. It doesn't have to be exact, it just needs to be in the ballpark.